All right, so, whoops, what happened? So this is like a shorthand drawing of what I just wrote. If you just sort of expand out in the inverters, you'll see again the phi's are basically inverted because this one goes to PMOS and this one goes to NMOS. Okay, and then basically the rest of these is, it's pretty popular to have multiplexers and resets, obviously. You always want to, by the way, here's another thing, never to get wrong. Every flip-flop you use in your design, make sure it has an asynchronous reset. Okay, so in terms of sequential circuits, if you remember two things, always use flip-flops, don't use latches unless you're a black belt, okay? And always make sure your flip-flops have asynchronous resets. Why resets? Because when your chip powers up, it powers up in some state. We don't know what state it's in, okay? There's like millions and millions and millions of flip-flops and other circuits on in your chip. When it powers up, when the power supply goes from 0 to 1, the chip hasn't started working yet. The inputs aren't connected to any node. There's no functioning whatever. So the chip can come up in like completely a brain boggled state. It can come up in a completely unknown state. Okay? So first thing you got to do is put it into a known state. Okay, and the way you put it into a known state is you reset all the flip-flops. That at least all the flip-flops in your chip all have zeros on their outputs. Okay, so that's a known state. So, and then remember that you have layers of flip-flops, and in between those layers, there's combinational circuits. So if you've reset these two layers and make sure all the outputs are zeros, then you know also what the output of the combinational circuits are. It's a known state, okay? So that's why, and believe me, I've been in chips, in fact, chips in JPL that people forgot to put resets on flip-flops, and basically you're sitting there turning on the chip, nothing happens. Turn it off, turn on the chip, nothing happens. Turn it off, turn on the chip, and then by the nth time you turn on the chip, and my chip might power up in some state that it likes, and now you're good. Like you don't want to put that in a spaceship and fly it out, right? You want to, every time you power it on, you want to know it's going to power on. Okay, so that's the reset. Now, the second question is why asynchronous reset? Asynchronous means regardless of what the clock is doing, the reset will reset your flip-flops. The reason for that is, remember that your clock network is also part of your chip. That means your clock network might also wake up in a weird state and not working properly. So I've also been part of projects where we had synchronous reset, and you're sitting there, you're resetting after reset, but it doesn't help you because you're not really resetting your chip because your clock network also just woke up and it's also in an unknown state. Okay, so make sure that you have. So anyway, a device. And there's ways of doing it, okay? So let me now go through CPP. Let's talk about some of this timing. I'm not sure, untitled. Give me a second, guys, make sure these things are complicated enough, I have to look at these timings. Okay, here we go. All right. Okay, here we go. Okay. So back to this, we have flip-flops and latches. So this is a flip-flop. So this is the safest approach. Okay. Latches only for the very experienced. And this pulse latches, I'm not even gonna bother going through. I've never seen a pulse latch in real life. It's just in books, as far as I've seen. I'm sure maybe it's used for something. Okay, so each one of these things has a different way of sequencing. Now notice that, so let's take a look at the case of the flip-flop first. So we have layers of flip-flop. We've only shown one flip-flop here. So one layer, two layers. And in between, you have a bunch of combinational circuits. Okay, so you're synchronizing them with the flip-flops. So, and in the case of a flip-flop, synchronization happens during the clock edge, in this case, the rising edge of the clock, meaning that when this clock goes high, whatever was at the input of this flip-flop right before this clock went high gets input to this combinational circuit. So at this point in time. And then the combinational circuit works through with whatever it's going to do with that input. The combinational circuit is a bunch of inverters, NAND gates, NOR gates, what have you. And then that stuff shows up on the output. Okay? Now, whatever that is gets sampled by the edge of by the following edge of the clock in the second flip-flop and gets passed on to the next stage. All right? So what that means is this combinational logic better get done before the second stage, the second clock edge arrives. So basically you have this amount of time, which is one clock period, to do whatever you're going to do in this combinational logic. If this combination, the delay through this combinational logic is longer than this clock period, then you don't know what's going to get sampled by that clock. It's some intermediate weird value will get sampled and sent to the next stage. So you don't want that to be the case. Okay. In the case of a two-phase latch, means you basically break this combinational logic into two parts, not necessarily two halves, but two parts. In this case, it's kind of shown as two halves. And you put latches with non-overlapping phases in between them. So during this phase, whatever's happening on this input during this entire phase goes to this combinational logic. It goes through, makes its way to the second latch. The second latch. Whatever's active, whatever is good here, when the second latch goes on, gets passed on to this guy and so on. Okay? You guys good with that? Now, to me, this seems like really frickin' dangerous, personally, okay? Because look at this. When the latch is high, when the clock to this latch is high, inputs, whatever's happening to this input, continue to get squirted into this combinational logic. During this whole time, these inputs keep coming through. It's not like I've blocked this flip-flop. Just make sure whatever was here is here, and I don't care what's happening here, I'm blocking it. Here, when the phi is high, whatever's happening, my input is still showing up in my combinational logic. Okay? So that means it's the designer has to make sure that things are stable, they're sort of stabilized here. Because imagine a case, okay? You have some delay through this combinational logic. Okay? At some point here, phi 2 turns on. That means whatever is at the output of this combinational logic will show up in the second combinational logic, right? Now let's say my inputs are still doing funky stuff. They're still moving around here when phi 1 is high. You guys with me? Right here, whatever is happening here gets put into this combinational logic, right? Right up till this point, as long as phi 1 is high, input's going through here. And there's some delay in this combinational logic before that stuff gets stable, okay? So you better hope everything gets stable before phi 2 turns on, okay? Or if you're in some intermediate value, you're kind of like screwed because you don't know what intermediate value goes through. So it's a lot more responsibility on the designer now to think about the timing. Okay, as the designer, you'll have to make sure these inputs aren't switching. Like the designer of this guy using the flip-flops, his inputs here can do whatever, like all sorts of weird stuff is happening. It doesn't get passed through here till the rising clock edge. So as the designer, you can just make sure you have the right inputs right at the clock edge and you're done. You don't need to care what happens before the rising clock edge, after the rising clock edge. You can just ignore those and move on. Here, you better make sure your inputs are doing what you want to do during this whole time. Okay? And remember, it's not just in a design. You don't have one input. You have thousands, hundreds of thousands of inputs to your combinational logic and sequential blocks. And that's why latches are really dangerous. If you don't pay attention to everyone, if you're using a latch and you don't pay attention to everything that's happening on these inputs, there's a chance something's going to happen that you did not intend to happen. Okay? Another thing, when your number of your gates increase, this is like really important because it's like you guys might still be thinking of a small design. Let's say if you have 20 logic gates, 50 logic gates, 100 logic gates, and 20, 30 inputs and outputs, you can still keep track of stuff. And you can't quite simulate every combination of everything that's happening, but still you can simulate a lot of stuff, okay? If you have a circuit block with thousands of inputs, let's say you guys have used Verilog simulation. Anybody used Verilog simulation? Some of you guys have used Verilog. It's a digital simulator. It's like Spice, but it takes a lot shorter to simulate. And you're just dealing with zeros and ones. It was great, right? You can simulate a lot of stuff. You can sit there and simulate a lot of stuff, but you will not be able to simulate every combination of stuff that shows up in this input. And whatever you haven't simulated, you maybe only be able to simulate like 0.1%, maybe 1% of the combination of things that could happen here. Because you're only looking at certain use cases. You're not looking at all the possibilities that could happen. Some combination of may show up here might make some glitches out here that will go forward. Anyway, just dangerous. I think it's just dangerous approach to use. So I'm going to steer you guys away from it. If it's a very controlled situation, again, like a pipeline, you have very few inputs, you're trying to do things in a very high-speed way, you can use them. But as a general rule, I think it's very dangerous. Okay, so let's just focus on these two possibilities. So although I keep saying don't use a latch, I'm still morally obligated to tell you guys how latches work. Okay, legally obligated. It's a card-carrying circuit designer. Okay, so now we talked about this is functionally what happens, but there are also delays through these circuits. Okay, it takes a certain amount of time between when the clock shows up and then when the output shows up on the output, or from when the input changes and it shows up at the output. Okay, so let's talk about all the possibilities. First, look at the flip-flop. Well, let's first look at the combinational logic. Okay, imagine if this is a NAND gate. Sorry guys, this thing keeps showing up on my screen. My Cal Poly login, dial in, whatnot. Okay, let's say, so for a second I'm going to talk back about combinational logic. And let's take a NAND gate, which is as simple as you get. A, B, out, VDD. And the table looks like this. And it's 1 and 0. Okay. Now, think about that if this is time and this is, like, say, voltages. The fall time is always the same because there's only one way to go from a 1 to a 0. Both of these guys need to be on. And both of these guys need to be off. So there's only one way to get from a 1 to a 0. Okay? But in a NAND gate, there's two ways to get from a 0 to a 1. There is the fast way, and then there's a slow way. What's the fast way? Well, the fast way is when A and B are both zeros, when they both turn on. I have twice the current. I've got two transistors pulling this node up, so it goes up really fast. Okay? And when only A or B is 0, so only A or B is on, only one of them turns on. So I basically pull this guy up at sort of half the speed is one way to look at it. Okay? So this is both A and B are 0, and this is either A or B are 0. So you can see that you actually, on the fall time, you always get the same delay from the input to the output of a NAND gate. On the rise time of a NAND gate, though, you can get two delays, the shortest delay and the longest delay. In the case of a 2-input NAND gate, there's just only 2 options. Okay? Imagine if you had a 3-input NAND gate, you really have multiple options, right? You have more options even, right? But there's always a minimum delay and a maximum delay. Okay? The maximum delay, so if you look at, this is like a piece of random combinational logic with some A on the input and some Y as the output. If my A is changing, there's a minimum delay for when it shows up on the output and a maximum delay when it shows up on the output. These are waveforms. This is how, like, people show these waveform functions. Are you guys familiar with these type of thing, circuits? So this basically, this guy says that A is changing in some way, and this says that the output is changing in some ways, okay? And the Y output can change if it's not a 2-input NAND gate, imagine if it's not even a 3-input NAND gate, imagine this combinational circuits are 1,000 gates, all of different types, and you're talking about input to output delay. There is a minimum time for, depending on the inputs, for the outputs to settle, and a maximum time. The minimum time is called, well, the maximum time is what you usually hear from, is called the propagation delay. And the minimum time is called the contamination delay. So minimum is called the contamination delay, the maximum is called the propagation delay. So for many years, even after I graduated, I was working, for many years, I only worried about propagation delay. Because I was like, well, delay is bad, so we want to minimize delay. So we want to minimize the delay through a combinational circuit, so I just worry about the propagation delay. Makes sense, right? Actually, it turns out that propagation delay is your greatest enemy. That can really kill your chip. I'll talk about it in a little bit, okay? So anyway, that's combinational circuit, that's inverters, NAND gates, NOR gates, exclusive gates, and so on. So let's talk about now sequential circuits, have their own delays, okay? So you have, let's first look at the time from the clock going high to when that clock going high shows up at the output. So let's say the output, it's stable, nothing's changing on the input, but so input's not shifting up and down, is just the amount of time for the clock to go to the output. The reason we don't care about the input going up and down is if the input's doing whatever around the clock, I don't care. I don't care, right? It's only the clock is grabbing whatever's the input is when it has that rising edge. So the only delay we care about as far as to the output is from the clock's rising edge to it propagating to the output, okay? So you have this CQ, the second CQ, is the clock to Q delay. Clock to Q. Q is the output of the flip-flop or latch. Clock is the clock. So it's clock to Q delay. The first C stands for the contamination clock to Q delay. So it's the shortest delay from clock to the Q. And the PCQ is the longest delay. So that's the propagation clock to Q delay. So those are those two times in a flip-flop, okay? Everybody clear why there's no D to output delay in a flip-flop? Because it doesn't matter. It doesn't matter. It's just whatever was on that rising edge of the clock. Okay? So, but we have two timings that are very important. If you guys do any kind of digital design, at any point you'll hear these things over and over again. Setup and hold times. Are you guys heard of setup and hold times already? So, and you'll hear them over and over. Your whole life is setup and hold times, okay? So think about it for a second here. So going back to our flip-flop example, remember that basically either this latch was on or this latch was on, okay? So when clock was low, D would show up to this input. This latch would make this latch transparent when clock was low. So this is clock. So this is latch 1 transparent. This is latch 1. And when clock went high, this is when latch 2 transparent and latch 1, you could call it opaque. Okay, and so we sampled whatever D was doing right over here. Whatever D was doing right over here is when we sampled. Okay, you guys with me? So D was during this time. This guy's on, so it's as if I'm putting D right here. And as soon as this edge goes up, I'm turning this off and turning this on and freezing that value at D. Okay? So setup time, this is like real components. There's delays through these guys and so on, right? So it takes a certain amount of time for whatever D is doing to show up in this point. Okay? So to make sure we don't get some weirdness, we're going to have to insist that the D stops whatever it is doing a certain amount of time before this edge. Otherwise, we're going to have some uncertainty. We don't know exactly what the delay is through here. From circuit to circuit, over temperature and temperature, etc. That's called the setup time. Okay? Means that D has to do whatever it's going to do a setup time before the clock edge happens. So if I go back to this, that's the setup time. Okay, D can do whatever it's going to do here, but it better settle down a certain amount of time before the clock edge happens. If it's wiggling around right here, if it's repeatedly going high, low, high, low, high, low, right up against this clock, I won't know which one I'm going to grab. So to get some certainty, I put a rule for this particular flip-flop, and I'm saying, you better stop whatever it is you're doing a certain amount of time before this to make sure I get a stable grab of whatever this value is. And that's called a setup time. Okay? And then furthermore, there is for the same kind of a similar reason, because the latch, you could get a situation where the first latch turns on, okay? You need to hold this value for a certain amount of time. So basically, after the clock edge to also get a valid value. So the setup time is the amount of time D needs to be stable before the clock edge, and the hold time is the amount of time D needs to stay stable after the clock edge for this flip-flop to work. So every time you design a flip-flop, you tell the user or you tell yourself if you're going to use the flip-flop, hey, this is like no D change time. This time is when D cannot change, this amount of time. Okay. So why is this important? Why are we talking about this? Because when you have, in this kind of circuit, you have a certain clock period where everything has to happen in this clock period, right? So stuff from here gets on this clock edge, stuff from here gets put in here, propagates all the way here, and it has to get here before this clock edge. You guys with me? Now, it doesn't have to get here right at this clock edge. It has to get here a setup time before the clock edge, right? Because I'm saying, don't be switching stuff around during setup time in this clock edge. So I'm eating a little bit into your clock period. I'm saying don't use that time. Okay, that's part of the so-called sequencing overhead time. So there's a penalty for me to use flip-flops and latches. The sequence overhead time is the setup time. Okay, so don't be switching your D around. Yeah, Francis.
Over the hold time, I'm not quite sure what you mean, but why is the hold time important?
The hold time is important because it'll become important during the contamination delay. So hold on to the hold time for a second. It's very, very important, but we'll take a look at it in a second. So that's the flip-flop. Okay, now let's look at the latch. Now the latch is not edge sensitive. It's either high value or low value sensitive for the clock. So let's look at this is a high value case. So basically you end up with some extra timing in the latch. So the first thing is the same as the flip-flop. There's a certain amount of time between when the clock goes high and the output shows up in your output. So this is the clock to Q delay for min and max. Okay, that's the same as the flip-flop. From the clock edge to stuff showing up at the output, you have a certain amount of time on a latch. Okay, and notice, by the way, so this is kind of schematically saying that this clock edge to this minimum delay is longer a little bit. I mean, they're schematically showing it than the latch clock to Q delay. The reason is in a flip-flop, you have more circuits, right? You have two latches back to back, so there's more delays and so on. So that's why people do sometimes use a latch, because latches tend to be faster than flip-flops if you're willing to take the risk. Okay. So, but in a latch, when your clock is high, if your D input is switching while the clock is high, it still show up on your output. Okay? So in a latch, you also have what's so-called D to Q delays. So your input D, that's this DQ, and you have a contamination delay and a prop delay also for your D input for a latch. This will take a certain amount of time for the input to get to the output. Okay, so you have to, that's an extra time. And then also the latches, those Ds need to stop switching around before when the latch turns opaque, and they need to hold for their value for a little bit after the latch becomes opaque. Okay, so those are the timing definitions for flip-flop and a latch. Are you guys ready for a little break? Yeah? Okay, let's take a little break and show up at 2:45. Yes.
Do you want us to email you the project, or do you want us to submit it to Canvas?
It'd be great if you could submit it to Canvas. I prefer you do that.
Just because, like, in the last class I had with you, you always wanted us to email it to you.
Yeah, I remember that too.
Yeah.
Yeah, so that's what we do.
Yeah, I figured just do it both. The reason I don't like doing that anymore is because I always end up screwing up like 2-3 people, like I don't copy them to right inbox of my email. And it's never catastrophic because they tell me, oh, I didn't get a grade. I submitted it. So can you go look back, and I find them. But anyway, so it's not going to be the end of the world if you guys can't submit it via Canvas. But I'm hoping it's gonna keep me from stuff from getting lost. Or again, it's not catastrophic. But, yeah. So anyway, you did both, you said,
Yeah.
or you just email? Yeah, it's fine. Either way, thanks. And I think Yash did. You sent me an email with doing both. Yeah. Yeah.
It wasn't submitting the PowerPoint, you wanted a PDF, I was like,
Yeah.
you want a PowerPoint or PDF?
I mean, either one will work. Either one will work.
Yeah.
It'll automatically come in a day after you apply. Interesting.
What's up? I didn't expect you to wait. Refund it. Yeah, right before the tip, I'm gonna get injured again.
What's a good deadlift? Is it like 2x your weight or something? I forgot what the
Good
good.
deadlift is no deadlift.
Yeah.
Just don't do it.
A lot of people think it's like too dangerous to be worthwhile, right?
Pretty much. Honestly.
I don't think so. When I was doing deadlifts, I really felt different, like good.
Yeah. Because I mean, it's a compound movement. Like it's
Yeah.
a full body workout.
Yeah.
It's great.
But anyway, yeah, but I guess it's pretty dangerous. I don't like squats. I didn't like squats. I haven't lifted weight forever, but as you can tell, can I or could I was pathetic because I'm heavy and I'm weak. That's a bad combination. So I could like do maybe like 2 and change or something like that. It was pretty pathetic. But like, but I think like aren't you supposed to be like don't they have these rules that, like you should deadlift 2x or something?
That's all lifter nonsense.
Yeah, it's bro science.
Yeah, that's science, exactly. That's the meathead logic.
Yeah. So anyway, I got to get back to lifting. But
Another saying like you should squat twice your weight. You should be able to bench like your weight or more.
yeah, Jesus Christ, no way.
I don't know.
I gotta lose a bunch of weight before I can do that.
No, you gotta use the weight to your advantage. The more body mass you get.
The more it is.
Once you're squatting.
Yeah. Have you guys ever met any like power lifters?
Oh yeah.
Yeah.
One of my coworkers competed in like the Vegas thing, and he placed like first on it. So he has a California world record or California record.
Wow. Yeah.
It's crazy. I think he can bench like 415 or something.
Wow. Is he a big dude though? Is he like
He's
is it?
5'7", 190 or 180.
Oh, it's not bad.
500? Like no 4, like 15, something like that. Benching.
Wow. Wow.
190 almost. He goes slow down and really fast. It's crazy.
Wow.
Yeah, I was working out.
Those guys are always complaining about having to eat too much, and I'm like, what are you talking about? I don't
Hey,
know.
you just start getting bored eating the 6
Yeah.
meals a day.
Yeah.
Oh, I can never do it. I think I did that for like 3 weeks.
Gotta get back to lifting, man. Lifting is so important. When I was like your age, I always thought like lifting was good, to look good and like athletic performance and that kind of thing. And like when you get to be my age, you realize is like you'll have, like you start hanging out with more, seeing more older people in your lives, like, you know, parents, grandparents, or maybe you guys already have them, whatever. And you realize, man, if I don't have muscle mass, like by the time you're 80, like you just won't even be able to get off the sofa. I mean, no joke. Like you just plain old will be, it's like necessary to lift. Otherwise, you're just gonna be like really messed up by the time you're, I mean, assuming you don't hurt yourself lifting, because that's the other way. You could be 30 and not be able to get off the sofa. So anyway, you don't want that.
My plan when I hit 70 is to start doing steroids. That's when
You got to start earlier than that, man. I don't know. Steroids? 50.
not to help with recovery and all that.
Yeah.
You lose all that youthful.
Yeah. Got to start hitting it. Do you guys watch Joe Rogan?
Yeah.
Yeah.
A little bit.
He's like proud of his TF. Is it doing his the
He does the growth.
TRT or whatever? Does he do growth hormones too?
Yeah.
Yeah.
That's why he's got that big gut.
Yeah. Gotta love these guys. Wonder what happens. Anyways, keep up the good work, guys. You don't wanna end up looking like me when you're in your 50s. Not good. Sad.
Fine.
Sad. Thanks. Sad excuse. Do you guys worry about how many pull-ups you can do?
I used to.
Yeah.
I just do weighted.
Yeah. Huh?
I have to do weighted because it's too
Oh,
long.
your body weight's too light? Oh, nice. That's a good
You
place.
gotta put on more muscle. You gotta bulk. Yeah, you're too skinny. That's good shit.
You're 180? Nice. What's your height?
5'10".
Nice. That's a good combo. I won't tell you guys what I weigh. It's pretty bad. It's ugly. It's all fat.
But didn't you do that like triathlon?
Yeah, I'm doing it, but it's really bad. You can imagine what me doing a triathlon looks like. It looks like a seal getting out of the water and waddling the rest of the way. It's pretty bad. Yeah. But I basically like finish. That's like my freaking goal. But man, it is ugly. It's an ugly situation when you're fat, because you're just like carrying all that weight for hours and hours and hours. So yeah, it's fine when you're in the water, but when you get out, you're just kind of like being the seal. Last one I did, I fell off my bike.
Oh, God.
I broke, like it was like sort of stress fractures. I broke like a few, like had a few broken stress fractures here. I just sort of like landed on my side, like halfway through the bike.
Did you
And
run
like,
over?
what's that?
Did you run over too?
No, thankfully I didn't. No, they keep the courses clean, so there's no, at least you don't get run over. That would have sucked. So I'm like, like I got, there's like skid marks on the road. I like landed, bumped my head a couple of times. So I'm like, oh shit, like this isn't good. So I'm like, and it's like all, like shirt's all stripped off and just bleeding. And my water bottles just went everywhere. And it's like, okay, this isn't good. So I got back on the bike, pedaled the rest of the way, and then got off the bike. I started running. And as I'm like running, like halfway through the run, like basically like pain is starting to like increase, right? So where it hurt when the fall first happened, now it's like spreading to my hip. And I'm like, oh shit, because like, your endorphins or adrenaline from the fall is like wearing out. And I'm like, if my hip goes, then I'm like really screwed. So I almost finished last. Might have been the 5th or 6th from last. sort of it's like bleeding and hobbling across. That's how that's my normal finish. So
Was everyone?
yeah, everybody was. It was funny during the bike. Everybody's like, "Go," because they're like, I'm like coming through. I look normal, and then I'm passing by. They say like, there's like I don't have any clothes here, and I'm just bleeding. So it was not good. Not good. That's my trial. Not good. Yeah. Anyway, so enough about me. Let's get back to flip-flops. All right, guys. So again, all this timing means this is like sort of eating into your clock period. This sequencing overhead is eating into your clock period. Okay. So in the case of a flip-flop, you need a certain amount of time. So starting with the clock edge, there's a certain amount of time for those inputs from that clock edge to show up on the input for your combinational circuits. And that's the clock to Q propagation delay. Okay, so the first thing is T, so I'm going to do clock to Q, and P is for the propagation delay. So it's this guy. Okay, so that you need that amount of time to get there. And then the combinational logic then does whatever the combinational logic's going to do. So this is showing stuff showing up here. So there's the propagation delay through your combinational logic. It goes up here. And then all of that better be done before the setup for your next clock. So if you can, what you really want, what you're really calculating is one of two things in a design, okay? In this case, you're calculating, so basically, let me put it this way. So T sub C is equal to, is better be larger than equal to whatever is your prop delay for your combinational circuits plus the propagation clock to Q of your first layer of flip-flops plus the setup time for this guy. Okay? So you are always trying to find out one or two things. One of them could be like, how fast can my clock be? Okay, given a certain design, how fast can my clock be? And that's when you use this equation. It's the same equation as this. Okay, or alternatively, they say, okay, your clock is this rate. This is the spec that the chip is. It has to run at this clock rate. So how much stuff can you cram into this combinational logic? So this is what this equation is doing. It's saying the prop delay through the combinational logic better be less than my clock period minus this overhead of these two states. Bless you.
Thank you.
Minus these two things. Okay? We're good? Okay. So now let's look at look at what happens if you got your chip back, okay, and you screwed this up. Okay, you made a circuit where the delay is too long in some combinational logic somewhere. Now remember, there are multiple, I don't know how many multiples of layers of sequential sandwiching combinational logic. So if you screw that up anywhere and this delay is this delay plus this clock to Q plus the setup delay ends up being longer than your clock period. Anywhere in that point, your chip won't run at that clock rate. Okay, seems bad. It's pretty bad. You didn't meet your specs, but it's not the worst thing that can happen to you. I'll describe to you the worst thing that can happen to you. It's still, because at least at that point, you have a chip that if all you have to do, okay, by the way, that's called a setup violation. Okay, it's called a setup violation. Because things did not get set up early enough for the next clock for this stuff to work. Which, yeah, go ahead.
So, if it's too much delay, will it skip that clock period and then it will then go into the next clock period and start it, or will it just not work at all?
It's, what you'll get is, you won't get valid results at D2. So you'll get something, you don't know what. Stuff is still settling, it's still going from 0 to 1, 1 to 0. There'll be some garbage. It won't be what you thought this combinational circuit would output.
Okay.
Do you see what I'm saying?
Yeah.
It could be anything.
Yeah.
And then the next clock, it'll be like another set of garbage coming through. Does that make sense?
Yeah.
It'll be like all sorts of intermediate results and glitches, and then it'll sample that. It'll sample that garbage and pass it on to the next layer. Okay? But again, like, nobody's gonna be happy, but still, the good news is if you just take that chip and reduce the clock speed, at some reduced clock speed, what you're doing is you're stretching when you reduce your clock frequency, you're increasing your clock period, means you're stretching this timing out. Okay? So let's say your chip was supposed to work at 2 gigahertz clock rate, it's not working. The first thing you do is you reduce the clock rate from 2 gigahertz to 1.5 gigahertz and see if it'll work. Okay? Because at some clock rate, if you got a setup violation, it will work. At some clock rate, every single flip-flop, combinational logic, flip-flop thing will have enough time for this stuff to happen when you have a setup violation. Okay? But of course, it's not a good thing, but like, it's not, at least you have something you can like debug, and now you can see where things fail. So what you do is, okay, this is the sequence of events. Almost every time. You get your chip comes back. Okay. Chip comes back, you plug it in, you go to your full clock speed, nothing works. Every single time. Okay. Then the next step is you go to half, a fourth, an eighth, whatever, however pessimistic, whatever time of night it is. The later it gets, the slower the clock rate. You plug it in till, and then most of the time, fortunately 99.99% of the time, it'll start working at the reduced clock rate. Okay? Whew. Like, thank God. Okay, 2 a.m., at least something's freaking working. Okay? And then from there, you start cranking the clock rate back up and start tweaking your circuit in like different ways. I'm not gonna go into all the dirty things you'll start trying to do to get your circuit to work, but at least you have something working and you can debug it. It's not just a paperweight. It's not just something that's not, if it's not giving you anything as an output, you don't even know what. So you can start cranking up the clock and you're still getting sensible results. And then you start getting sort of at some point some funky results. And all of that can help you at least figure out which one of these many places in your chip where you have this stuff, like which one of them is failing. At least you can, it'll take you many days, weeks to debug, but at least you can sort of play around with it. And between what you're seeing in the lab and simulations, because you still have your simulations, right? From the simulations, you can say, I'm seeing this in the lab. Let me stress my simulation. Let me increase my delays in the simulation over here. Does it match? It's just a debug process. Okay, so who knows where it will lead you? Yeah. But
Is there like a certain, I guess, buffer? Like, do you want like the time clock to be 20% greater than your total time delay for that to work? Is there like a certain percentage you should be considerate of?
20% is good. Yep. That's called your margin.
Okay.
Good, damn good question. Always put in margin, right? If your spec is at 2 gigahertz, do all your simulations at 2. You better make sure your circuit works at 2.4 gigahertz, say. Okay, so 20% margin is good. By the way, the same goes for everything in engineering life, right? And it's never enough, right? You'll still be in trouble with your 20% margin. If you think as your schedule, you'll get the chip done in 6 months, make sure you tell your manager 7, or at least start a negotiation, they'll start pulling things back, or tell your customer 7, right? So power consumption, all these things. Sometimes you are within that margin, and sometimes you are sadly mistaken. Okay, sometimes things take twice as long. Sometimes things cost 3 times as much. Sometimes your margin needs to have been 50%. But anyway, so you can do what you can do. Okay, so that's the maximum delay. Again, I'm emphasizing because there's a punchline coming here, going back to Francis's question about what is, if this is the second worst case situation, what is the first worst case situation? The first worst case situation, I'm going to go over to here, is the worst case situation is called a hold time violation. Okay? And that's what happens in the other end of this extreme is, let's say you have a layer of flip-flops and you have a set of combinational logic till you get to the next flip-flop. Okay? So the same situation as you had before, but let's say this combinational logic is actually very small. You don't have that much in this layer. Okay? For whatever reason is. So there is a possibility if this stuff, I'm not sure I do this master way. If this delay is too short, it's a possibility that stuff will go from the rising edge of this flip-flop. This data will race through to here, go through here, and show up to this point before the whole time of the second flip-flop. Remember, you do not want anything changing for a certain amount of time after the clock edge arrives. That's the whole time. Okay? Basically, if something happens, so you have your clock edge, and you have D. If this is the setup time, this is the whole time. So if stuff happens in D before the clock, this stuff can get grabbed on to by the flip-flop accidentally, right? You guys see the setup time issue? That if you were going this data, if it's switching too close to this edge, you can end up grabbing something you did not intend to grab. Okay? Usually it means you didn't grab what you wanted to grab, like you grabbed a value before it. Okay? Let me draw something for you guys. I don't know if it'll help or hurt. So remember, the flip-flop input has these pass things. So if D is switching out here, you're counting on it going over here. So you got the delay of this guy, and the delay of this inverter to worry about. If you start getting this D in terms of time too close to the clock edge, that D that you just updated doesn't have enough time to get to here. Okay, so a previous value, an unintended value of D from back here or whatever gets latched onto the second latch. Okay, not the one you intended. Okay? And the hold time, what happens with the hold time is if your D is shifting close enough to this output point, so this is your rising edge of your clock, and your D is still shifting over there, there is a chance that your clock is delayed with respect to how long it takes. So let's say D gets here super fast. Okay, if D shows up here super fast, it's possible your clock was delayed with respect to the D, and it's possible that guy gets through your latch. Because you could have delays in your clock path, or you could have delays in your D path. Francis, you look very confused. You don't see how the clock could be. Okay, let me tell you guys this. So remember that your clock comes into your chip and gets distributed all over. Okay? So when I'm drawing a clock here and it's the same as this clock, that's only in an ideal circumstance. Okay? That this clock is the same as this clock. There could be like any kind of delay. There's not like the absolute value of clock sort of depends on where you are in the chip. And the relationship between that absolute clock and the D therefore depends on where you are on the chip, if that makes sense. So imagine if you're here and your clock is going to a flip-flop here, whereas imagine your clock does a bunch of other stuff, and, oops, does a bunch of other stuff and goes to a clock on the next D. And then imagine if this D, this Q is driving this D. There could be a big delay between, like D could get there a lot faster than clock, possibly. Does that make sense? And you just don't know, like you could say, well, who would do such a moronic thing, right? When you know this Q is going to here, who would do this idiotic thing, right? But remember that we're talking about billions of transistor gates, paths, whatever. You are not keeping track of every one of these paths. A bunch of these paths, like 99.99999% of these paths are being created by a computer that's trying to cram the stuff any way it can in there, okay? You've told it, the thing is very smart, but you've also given it constraints of area. You have only a certain number of metal lines to connect all this stuff together. It's like a two-dimensional place where if you make a decision to put these two circuits next to each other, then that third circuit might also want to be close, but guess what? That real estate's already taken, so it needs to go over. So this computer-aided software is playing sort of an n-dimensional game of optimizing everything and does a really good job of, if you have billions of nets, billions of lines in your circuit, it's going to do a really good job in billions of those cases, but there's always thousands, so a small percentage ends up being thousands of cases where it's going to have to either be forced to do something nonsensical or does something nonsensical because it's not a perfect algorithm. You guys with me? So the beauty, thank God, is in a design is once you're done with the full activity, the first draft of your chip, you've done all this stuff and you get the results back from your simulations, you only get thousands of hold time violations and thousands of setup violations, only. Right? Because you got to imagine that's still a small percentage of all the things that you have in your circuit, but it still ends up being thousands. Okay? Are you guys, does this kind of make sense? Why you might need to have a hold time? Yeah.
But so, we were talking about setup time earlier, how they need to stop switching by a certain time. If the value is already held, why does the flip-flop have a problem? Because shouldn't it just wait for the rising edge to come in and then take that value?
Yeah, so, but see, you're thinking of it's being held by what time though? By the clock edge.
Yeah.
So, but when is the clock edge really coming there?
This is going to come later. So will it not?
It's, it's possible to come later. It's also possible it's going to come sooner. Because I could have easily drawn it the other way, right? I can just draw, let me draw you the next layer. Okay, so now this clock is going to get to the next layer a lot faster than this clock. So this D is going to show up here. God knows, like it may well show up after when you expect the clock to be there. Does it make sense?
That one.
So also basically this is going back to margin. You're buying yourself some timing margin around the clock edge. The clock edge is when you want nothing to happen around the clock edge. Either before the clock edge, slightly before the clock edge, or slightly after the clock edge. You don't want anything happening around that very critical time. Okay, so maybe that's another way to look at it. I don't know. So, but does it make sense? Stuff that the amount of time you want to make sure you keep things from going after the clock edge is just called the hold time. And the amount of time you want stuff not to be switching before the clock edge is called the setup time. Does that make sense? Okay. So, like now, okay, imagine if you have a hold time violation. Okay, a hold time violation is, again, usually happens when there is a small combinational circuit between. So this delay is very short. It makes the situation much worse. So basically you could get a situation where you could get a clock. This clock could happen. The D value gets to Q, gets to this D2 during the whole time of D2. So, sorry, another thing that gets confusing is we're thinking of this as if this clock edge first shows up here and then it shows up here, right? It's not the case. In this clock edge where stuff's happening here, this guy is also seeing that same clock edge. It's just sort of trying to deal with something that happened in the previous time to the previous sequence time, right? So this guy gets a clock edge the same time as this guy gets the clock edge. But you'd like your data to work its way through this for this guy's next clock edge. That's what you'd really like to happen, right? Because you want this sequence and you want the next sequence. If this delay is short enough, what happens is you'll end up throwing both in the same time sequence. Does that make sense? Yeah? No? What you guys have a question about? This is really, really important because this is like really a problem. But let me first tell you what the problem, why this is worse than the setup problem, is because notice that this is a problem with the same clock edge. Okay, the setup was from clock edge to the next clock edge. So by reducing the clock frequency and increasing the clock period, I could move those two clock edges away from each other and get the chip to work. Okay? This problem is happening on the same clock edge, so it doesn't matter what I do to the clock frequency. I can't move that. It's the relationship of the clock edge with like itself. So once you get a hold violation, you'll always get a hold violation. There's no changing the clock to fix it. So that's when you get a paperweight. Your chip is just not going to work when you have a hold time violation, and there's no way to get it to work at any clock speed. And so there's no way to debug except to go, my chip doesn't work. And now I have to go back to my simulations and try to figure out where I screwed up without having any lab results to compare with. And this, again, in the set, imagine how much more difficult debug gets if all you know is your chip has a hold violation and you just have no idea. But let me ask, this was one question came up before. Let me try to,
So,
did you?
Yeah, so for flip-flops, what's beating the hold time is the flip-flops input, right?
Yeah,
That's what needs to beat the hold time.
that's
As
what
long as
needs to be.
that's stable before the end of the hold time, then you're good.
That's good. Yeah,
That's pretty much it.
that's pretty much it.
Yeah, makes sense.
But anyway, you have a chance again when you have, so this happens, I'm not gonna get into like a specific case, but there is definitely one very specific case. So you have this, well, I'll just mention it. So you can imagine a multi-billion transistor chip is very hard to test, because when you get that chip in production, okay, you have two types of tests. One is called the characterization test. You get the chip back, the design engineers are sitting there for weeks and months, making sure the chip meets spec, okay? But after that, every chip that comes off the factory line, you better test every single chip to make sure nothing's broken in that chip before you ship it to the customer, okay? And now you want that test time to be very short. I'm talking about minutes, because that test equipment is a capital expenditure. Every hour spent in that test equipment is hundreds of dollars. And you divide that by that time, that's an extra expense of that your product will have. So you want to make that test time really short. So to do that, you do something called a scan chain in your circuit. I won't go into the details, but basically it looks exactly like this. It looks like a giant snake of flip-flops sort of hooked up together, and like you can really have a bad situation. So sorry. So what was your question? Sorry.
I was gonna ask, how do you know you have a whole time problem with your chip, or you just don't, or you just fuck it up?
Well, one good indication is regardless of your clock rate, that it won't work. That's like one very good indication. Okay? So you gotta, because you also have to imagine all the stuff that came before that point for you to be looking at that chip, right? Assuming you didn't do really stupid things before that point, you would have spent months and months before the chip even went to get manufactured or built, before the prototype's built, simulating that chip. You put a synchronous reset on every flip-flop in that chip so you know how it comes up, right? You built it using CMOS logic that's got good noise margin. You built your test board with, low noise and all that kind of stuff. So you're kind of like trying to rule out actual noise causing a problem. So you're trying to rule out noise causing a problem and a functional error from causing a problem. I mean, it could be that you screwed up your combinational circuit, right? But even if, think about this, even if you screwed up your combinational circuit's functionality, for most of those combinational circuits, it'll give you some garbage output, but it'll give you a stable garbage output. It'll give you the same stable garbage output from power up to power up. You'll get the same junk, and you'll go, okay, well, at least stable. And it'll be valid. You'll actually get valid, zeros and ones and stuff. It just won't be what you want. Okay? A hold time violation, typically, a lot of times, it won't be stable because you're almost by definition, you're kind of in an unknown state, and you're feeding that unknown state next to another layer. And this is part of the problem, is that part of the debug process, okay, is that these margins, you need these margins because of delays of inverters and circuits, right? Whether it's the clock driver, God damn it, why are, sorry. Damn it. It's probably gonna go do some squats or something. So depending on the delay, you're gonna get a problem. And one of the thing, another knob besides your clock that you start playing with when you're debugging a circuit is your power supply. When your power supply is, so remember that you have about a 10% high and low margin on your power supply before your transistors blow up. Okay, so if your supply is 1.1 volt, you can take it to 1 point, whatever 10% of 1.1 is 1.22 volts on the supply, or you can take it to roughly 1 volt on the low supply. Okay? And remember that your gate source voltages are basically dependent on your VDD, right? Whatever is your VDD gives the gate source voltage of the next stage, okay? And your transistor currents are sort of square law dependent on that increase. So if you're increasing your gate source voltage a little bit, you're probably increasing your current through your transistors even more. And now remember that the delay of your gate is depending on how much current charges and discharges the capacitance. You're not changing the capacitance much when you're increasing or reducing your power supply, but you're increasing or decreasing the current that's charging or discharging the outputs of your gates quite a bit. Okay? Which means you can play with your delays through your stages. You can make the delays higher or lower by increasing or decreasing your supply voltage. Okay? It's not a good thing to do, but this is the kind of stuff you do in the lab. You start playing around with, I'm going to try to speed things up a little bit, slow things down a little bit by playing with my supplies. Okay, let's see if anything works, does anything get stable. The next place you look at, like I had a friend that no matter what would happen, if a chip was not working, he would take a dust can, spray can, those spray dust cans, flip it upside down and spray the chip, because that's sort of like freezing the chip, because the delay is also the least at low temperatures. At low temperature, your currents are also sort of the maximum value. It just turns out as your temperature increases, the delays increase generally. So that's another thing you do. You start like playing around with the temperature. You're just sitting in the lab trying to like get the chip to do something with a known change. The other thing you do is like another favorite thing is hair dryers, right? You grab a hair dryer. Of course, you're in the lab, right? So you don't have really decent equipment. And it's usually late at night. So I don't know why you just have a hair dryer from the previous time you screwed up. You start heating up the chip. Okay, so you're trying to figure out like what happens. Okay, so you got that. So now you got your chip, you got your clock, you got your power supply, and you got kind of your temperature to some extent. You got those four things that you're adjusting or playing with, trying to figure out what that means. And then most importantly, you still have your simulation database. Okay? So let's say you have a chip that works at a high supply and not a low supply. Okay? So now you can go simulate your circuit at the low speeds and see, or sort of, we haven't gotten to the simulations yet, but when you get simulation models, you get slow simulation models, fast simulation models, whatever. So every gate has several delays that the factory is telling you, like this is a slow version, this is a fast version. So you can make these changes in your simulation and see if it breaks, and see if it breaks in a way that's the same way that things not working in the lab. So it's like you got a few tools, you got your simulation, and it's like the best of times, it's like the worst of times. It's the worst of times because you got a chip that's not working. It's kind of the best of times because it is kind of like fun. You're kind of like trying to, as long as it doesn't take too long, right? And as long as your management is not a pain in the ass, okay? So, just as an anecdote, when we started our company, was like, we started our company in October of 2001. It was right after September 11th. And simultaneously, what happened before September 11th, which was even worse for a startup company, was the tech bubble, the internet bubble burst around 2000, 2001 timeframe. So that was the previous recession of, like 2008 was bad. For tech, 2000 I think was worse, is when the internet bubble burst. Okay. So long story short, we were starting up this company and we had exactly one customer, right? So it's not like customers are beating the door. It's like a bad time in the business. We have one customer, and you can imagine like everything depends on this one customer. So I think it was 6 or 7 or 8 months later, we've got our first chip is back. And we're in the customer, and we don't have our own lab, right? We're just like 3 people in this company. We don't have a lab, we don't have anything. So we're testing this at the customer site, worst place in the world to. So we plug in the first chip, and me and another guy, he was a friend of mine, but he worked for our customer. He was their engineer. Turned it on, we both actually saw a spark, okay, before everything died.